Hello, my name is Haley, and today we're going to be talking about nucleophilic aromatic substitution. So first, let's kind of cover what's even going on in this reaction. So you're going to start with some sort of aromatic compound. I chose to use a benzene because benzene is really one of the most common aromatic compounds you're going to be using, but any of your aromatic compounds that you've learned would really work well and be fine. So on your aromatic compound, you're going to have a halogen, and this halogen could be an F, Cl, Br, or an I. And then at either the ortho or the para position, you're going to have some sort of electron withdrawing group. And then you're going to react this aromatic compound with a strong nucleophile. A strong nucleophile could include NaOH, NaOCH3, whatever fits the reaction that you're trying to do. And so essentially what's going to be happening is the nucleophile is going to replace this leaving group. So right where we had that halogen, we're now going to have our strong nucleophile, and then our electron withdrawing group is just going to stay the same. So now that we understand what this reaction is all about, let's go into the mechanism. So we're going to start with our aromatic compound and our halogen. So in this case, we can use chlorine, but again, you can use any of these halogens. And then we're going to use our electron withdrawing group at our ortho or our para position. So in this case, we'll do NO2 at the ortho. Now we're going to react it with our strong nucleophile. So in this case, we'll just use negative OH as an example, a little bit of heat. So the electrons on this OH are going to attack at that same position that we have our Cl. And then these electrons are going to push over to that position. I don't know if you can, maybe I'll highlight it, to this carbon is where our electrons are going to go. And then we're going to end up with what's known as our sigma complex. So we're going to have our halogen, our Cl, and we're going to have our nucleophile at that same position, and then our electrophile unchanged, and then our lone pair of electrons right there. And then these two bonds are going to stay the same. So this sigma complex is really going to be our rate determining step. And so once we have this sigma complex, these electrons are going to push back in to reform this double bond, and we're going to kick off our leaving group. And that's going to bring us to our product, which is where we've replaced our halogen with our nucleophile. Luckily, this is one of the mechanisms that's really more straightforward and not a 15-step mechanism. So just kind of a recap. The 3 steps are: 1, the nucleophile is going to attack the sp2 carbon with halogen, or, oops, oh no, we'll say with leaving group. Second, we're going to form our intermediate, which is going to be our sigma complex. And then third, our leaving group is just going to leave. And then we have our product. So now let's talk about why our electron withdrawing group needs to be at either the ortho or the para position. So let's start with ortho. So when we're in ortho, we're able to take this lone pair of electrons and push it over here to the nitrogen and kick these electrons up. And this is going to stabilize this negative charge. This nitrogen has a positive charge. It's super, super happy to accept this negative charge. So this is going to be a great way to stabilize the negative charge. And as always, our most stable intermediate is going to be our preferred intermediate. And with our para position, we can actually push these electrons down. This is going to kick over. And then we're going to end up with our lone pair at this carbon. And then we can do the same thing where we push these electrons over and kick them up. But what if our electron withdrawing group is at the meta position? So at the meta position, we're not able to push these electrons onto this carbon. Instead, through resonance, they're going to want to jump right here. And from this position, there's no way that they can make it over to that nitrogen. And there's no way that it can be stabilized by this electron withdrawing group. So if you have your electron withdrawing group in the meta position, this reaction is really not going to go forward very well because the rate determining step is the formation of the sigma complex, and that's so slow. Okay, so let's also talk a little bit about our halogens and which halogen is going to be the best leaving group. So as we know, the sigma complex formation, sigma formation is the rate determining step. And because fluorine is the most electronegative, this is going to give you the fastest reaction and is going to be your best halogen, your best leaving group in this case. And I know it's a little funny because usually fluorine would be the worst leaving group and something like iodine or bromine would be a lot better. But in this case, because fluorine is so electronegative, it can increase the electronegativity of the electrophile, which is going to be your aromatic ring with your halogen and your electron withdrawing group. And this is going to push your reaction forward a lot more quickly. So now that we understand this reaction, let's see an example of what this could look like, on an exam or in a problem. So say we're starting with just a plain benzene ring. And we're wanting to go to this molecule. So let me move this down so there's a little room. So we would start by adding one of our halogens. In this case, let's add chlorine because we know that chlorine is going to be one of our faster halogens, and it's also a halogen that we know how to add. So Cl2, Al, Cl3, and that's going to give us our benzene with a chlorine. And then in order to do our nucleophilic aromatic substitution, we want to go ahead and add our electrophile. So in this case, let's add NO2 again because it's a pretty good one for this reaction. H2SO4, and that's going to give us Cl, NO2. And then, let's see, I'm going to draw it going down. And then we can do our nucleophilic aromatic substitution now with our NaOCH3, a little bit of heat. And this is going to give us, oops, not Cl, OCH3. This is where our nucleophile has replaced our leaving group and our electron withdrawing group. And we could even take this one step further if we wanted to, and we can change this NO2 into an NH2 with PDH2. And then that would give us OCH3 NH2. All right, so the reason that we turned this last reaction all the way to an NH2 instead of leaving it at an NO2 is to lead us into our Sandmeyer reaction. So our Sandmeyer reaction is going to start with an aniline, which is going to be our benzene with an NH2. So I'll write that, aniline. And then we're going to first react it with maybe I'll color code this so you can see the reactants. NaNO2 and HCl. And this is going to give us our diazonium salt. So it's going to be benzene, nitrogen, triple bonded to a nitrogen. So diazonium salt. And then there are kind of three courses of action that we can take once we have this diazonium salt. So we can take this, sorry, ignore that. And we can first react it with CuCl. And this is going to give us, in place of those nitrogens, a chlorine. Or we could react it with CuBr. And just like we saw with the chlorine, we're going to replace those two nitrogens with a bromine. Or, alternatively, we could react it with an H3O+, and this is going to replace those two nitrogens with an OH. So now that we kind of get what the Sandmeyer reaction is, let's go into the mechanism. All right, so let's look at this NaNO2 over HCl reagent that we're going to be using. So we can draw NO2 like this. We'll have our O, the negative charge, single bonded to our nitrogen, which is double bonded to another oxygen. And when we react this with two equivalents of HCl, we're going to get H2O, which is going to have a positive charge, single bonded to the nitrogen, double bonded to this oxygen. And then the lone pair on this oxygen is going to kick over, and it's going to cause this OH2 to leave. And this is going to leave us with an N triple bonded to an oxygen, or it could also be drawn as positive charge on the N, double bonded to the O. And this right here is very reactive. So now that we have this NO, we can react this with our aniline. So let's take our aniline, which is, remember, this NH2 on a benzene ring, and we're going to react this with this NO. And so this lone pair on the nitrogen is going to come over, tack here. And that's going to leave us with this right here. An N, it's two H's, so our NH2, single bonded to this N, which is double bonded to this O. And now it's this nitrogen that carries that positive charge. All right, so now that we're here, we don't want to hold on to this positive charge on this nitrogen. So we're going to use a little bit of water, H2O, to grab one of these hydrogens and give those electrons back to the nitrogen. So now we're going to be left with our nitrogen with one H, single bonded to a nitrogen, double bonded to an O. And because this water just grabbed this hydrogen ion, now it's H3O+. And so our H3O+ in solution is going to protonate this oxygen. And that's going to leave us with our N with an H. Oops. No positive charge there. Bonded to an N, double bonded to an OH. that leaves us with a positive charge on this oxygen. This oxygen does not want to have this double bond. So instead, we're going to form a double bond between these two nitrogens and have a single bond with that OH. So it's going to look like this. This still has its H, double bonded. Now we have an OH here with a single bond. So now we have this positive charge on the nitrogen. We don't want to leave a positive charge there. So again, we're gonna, sorry, this is so messy. We're gonna use water and we're gonna pluck off this proton. And that's gonna give us N double bonded N OH. And so we're almost there, but we know that we want to have a triple bond between these two nitrogens, and we don't want to have this OH anymore to get our diazonium salt. So with this H3O plus that we've just generated, I'm actually going to go to the next page. So we're right here with this right here. So we're going to use this H3O plus that we just generated with our water in the last step. And that oxygen on the OH is going to grab a hydrogen, push that over, and give us this OH2, which is awesome because we know that OH2 is a pretty good leaving group. And now it's super easy. The lone pairs on this first nitrogen are going to kick over, make a double bond, and cause this OH to leave. And now we have our diazonium salt, which is ready to be reacted with our CuBr, CuCl, or our H3O plus in our Sandmeyer reactions. So now that we get the Sandmeyer reaction, let's do an example where we're going to use this reaction. So say we're starting with just a plain old benzene. We want to turn it into a benzene with a bromine and an OH in the para position. So we're going to come down here. And first, we're going to start by adding our bromine through our Br, Fe, Br3. And that's going to add right here. I mean, really, it would add anywhere, but since we want it in this top position, we'll just put it here. And now we want to add our electron withdrawing group. So let's do our H, NO3, H2SO4. And that, because remember, bromine is an ortho-para director, even though it's deactivating, it's still ortho-para directing. We're going to add our NO2 to this position. And then remember, we can turn our NO2 into NH2 with PDH2. So now we have bromine and an NH2. And this sets us up to do our Sandmeyer reaction. So I'm just going to move this down here to make it a little bit more neat. So remember, the first step of our Sandmeyer reaction is converting this alanine right here, or aniline, sorry, into our diazonium salt. So we're going to do NaNO2 and HCl. So now we have our bromine, and then we have our N triple bonded to our N. This is going to be our DZ salt. And now we can finish our Sandmeyer reaction with H3O plus and convert this N triple bonded N into an OH. And we still have our Br right here. All right, now let's do one final reaction where we can see the Sandmeyer. So say we're starting with our plain benzene And instead of adding to the ortho-para positions, we want to have, oops, let me move this down. We want to add a group to the meta position. Now remember, chlorine and bromine are both ortho-para directors, not meta directors. So we can't just add one and then add the other. We have to go through our Sandmeyer reaction. So we would start by adding a meta director, which would be our NO2. So we can add HNO3, H2SO4, and that'll give us our NO2 right here. And since this NO2 is a meta director, let's go ahead and add our bromine. So Br2, FeBr3. And now we've got our NO2 and our Br in the meta position. So now we can get ready to do our Sandmeyer with our NO2. So let's go ahead and turn this NO2 into our NH2 to set us up for the Sandmeyer through PdH2. And so now we've got Br, NH2, our aniline. And so remember, the first step of the Sandmeyer is to convert this NH2 into an N triple bond N through NaNO2 and HCl. So here we are with our N triple bond N, Br. Now we can do our other Sandmeyer reaction with this CuCl, convert this, oops, that's a triple bond, this N triple bonded N, our DZ salt, into our desired product of Cl here and Br in the meta position. You could also do it the other way, where you first add the Cl in the meta position, and then you convert through Sandmeyer to Br. Either way would work.